Welcome back to the Deep Dive, where we take a stack of chemical concepts and, well, distill them into the essential knowledge you need. Today, we're jumping into the fascinating world of halogenoalkanes molecules that live this incredible double life.
It's a real study in chemical contradiction, isn't it? I mean, you have compounds in this family that are so perfectly inert, they can be safely used in the human body as anesthetics, things like halothane.
Right.
And yet other very closely related compounds, the CFCs, were so reactive up in the atmosphere that they almost destroyed our planet's ozone layer.
That duality is the perfect hook for this. So our mission today is to unlock the core chemistry here. We want to understand how we make them, why that carbon-halogen bond is so vulnerable, and the two major reaction pathways they follow, substitution and elimination.
And we can start with those safe applications. Take halothane, for instance. That's 2-bromo-2-chloro-1,1,1-trifluorothane. It is. But its safety lies in those three incredibly strong carbon-fluorine bonds, the CF bonds. They just require a huge amount of energy to break, which means the molecule stays stable and chemically inactive inside the body.
And that was a massive improvement over older anesthetics like chloroform, right? Trichloromethane.
A huge improvement. Chloroform just didn't have that same internal stability.
But then we get to the environmental paradox with chlorofluorocarbons, the CFCs. At ground level, they were perfect. Non-toxic, non-flammable.
And completely unreactive. That's what made them ideal for refrigerants and aerosol cans.
But that inertness was also their downfall.
Exactly. Because they didn't break down. They just hung around in the atmosphere for decades, slowly rising up to the stratosphere. And once they get up there, the sun's high-energy UV light provides enough of a kick to snap the weaker carbon-chlorine bonds.
When that CCl bond snaps, it unleashes a real molecular villain, the chlorine-free radical.
It's incredibly destructive. These radicals are highly reactive, and they act as catalysts. Our sources estimate that just one single chlorine radical can destroy up to 1 million ozone molecules.
1 million.
Up to 1 million, before it's finally removed from the atmosphere. That's how we got the hole in the ozone layer, that rapid catalytic cycle.
So the solution chemists came up with was brilliant. Hydrofluorocarbons, or HFCs.
Yes. HFCs like CH2FCF3, they break down much, much faster because they have hydrogen atoms. This lets them decompose lower down in the atmosphere, so they never get a chance to release those destructive chlorine radicals up in the stratosphere.
And that's allowed the ozone layer to start its recovery.
A slow but steady recovery.
Okay, that story really shows the power of bond strength. So let's switch gears. Instead of breaking them down, how do we build them up? What's in the chemist's toolkit for making new halogenoalkanes?
Well, before we can break them, we have to make them. And there are generally three main ways we do this. The first is free radical substitution of simple alkanes. You typically use chlorine or bromine gas and zap it with some UV light to get the reaction started.
So like ethane plus chlorine gives you chloroethane.
Simple as that. The second route uses starting materials that are already reactive, alkanes.
Of course, the double bond.
Right. We use electrophilic addition. You can react an alkene with a halogen like bromine or a hydrogen halide gas. It happens quite easily at room temperature. Ethene plus bromine, for example, quickly gives you 1,2-dibromothane.
And the third main way substituting alcohols is where it gets more strategic. The sources list 4 different reagent combos. Why so many choices for just swapping an OH group for a halogen?
It often comes down to things like purity and yield. You can use hydrogen halides directly, or you can generate them in situ right there in the flask using a potassium halide and an acid.
Okay.
But then you have the other more complex reagents. PCl3, PCl5, or my personal favorite for this, thionyl chloride, SOCl2.
Why is that one your favorite?
Because it's just so elegant. When you use thionyl chloride, your only side products are sulfur dioxide and hydrogen chloride. Both are gases. They just bubble out of your reaction mixture,
Leaving behind a much purer product.
Exactly. It makes the cleanup so much easier, which is a massive advantage in any large-scale manufacturing.
Efficiency isn't just the reaction, it's the cleanup too. Makes perfect sense. Okay, let's quickly classify these molecules because this seems to dictate everything that comes next.
It absolutely does. We classify them based on the carbon atom that's bonded to the halogen. If that carbon is attached to just one other alkyl group, we call it primary. If it's bonded to 2 alkyl groups, it's secondary. And if it's bonded to 3 alkyl groups, it's tertiary. And you have to remember that distinction, primary, secondary, tertiary, because it's central to the reaction mechanisms.
All right, let's get into that reactivity, section 16.2. Halogenoalkanes are way more reactive than alkanes, and it all comes down to bond polarity.
Indeed. The halogen atom is just far more electronegative than the carbon it's attached to, so it pulls the electron density in the bond towards itself. The halogen gets a partial and negative charge, a delta minus.
And that leaves the carbon atom partially positive, delta plus.
Precisely. That delta positive carbon is now electron deficient. It becomes a prime target for a nucleophile.
A nucleophile being any molecule or ion that can donate a pair of electrons.
You got it. And that defines our most common reaction type, nucleophilic substitution.
So first up is hydrolysis, which is just a fancy way of saying we're forming an alcohol. We can use aqueous alkali.
Right.
Or just plain water.
Right. If you use aqueous sodium hydroxide, NaOH, and heat it up, the hydroxide ion, the OH, is your nucleophile. It attacks that delta positive carbon and kicks out the halogen. So bromethane becomes ethanol plus a bromide ion.
And you said using pure water also works, but it's much slower. Why, the huge difference in speed.
It's all about nucleophilic strength. The hydroxide ion has a full, concentrated negative charge. It's a very powerful electron donor. The oxygen in a neutral water molecule only has a partial negative charge.
So it's just a much weaker attacker.
Much weaker, much less effective.
And we can actually see this in the lab, right? With aqueous silver nitrate.
Yes, it's a great experiment. As the reaction happens, the halogen leaves as a halide ion, which then immediately precipitates with the silver ions. You just time how long it takes for the precipitate to appear. White for chloride, cream for bromide, pale yellow for iodide.
And what does that tell us?
The observation is crystal clear. It leads us to a really key conclusion. Reactivity is determined not by the bond's polarity, but by the bond's overall strength.
Please, I have to stop you there, because that's a point that can really trip people up. The reaction is started by the polarity, but the rate, how fast it happens, is all about strength. Does the bond strength always win out?
In this case, yes. The trend is that iodoalkanes are the most reactive, then bromoalkanes, then chloralkanes. Fluoralkanes are the least reactive by far, and if you look at the bond energy values, the CI bond is the molecular weak link.
So it's the easiest to break.
It's the easiest to break heterolytically. It's about half the strength of a CF bond, so even though the CF bond is the most polar, it's just too strong to break easily. The weakest bond always goes first.
The weakest link in the chain dictates the speed. Perfect. Okay, two other quick substitution reactions. For an alcohol, you use OH. But to extend the carbon chain, we need a special tool, the cyanide ion.
That's right, forming nitriles. It's incredibly useful. You use an ethanolic solution of potassium cyanide, KCN, and heat it under reflux. The cyanide ion, CN, substitutes the halogen. And the magic here is that the cyanide ion itself has a carbon atom, so you lengthen the chain.
Bromethane becomes propanedietrile. You add a carbon.
You add a carbon. And the third type creates amines, using ammonia. Yep. Ammonia acts as a nucleophile, replacing the halogen to form a primary amine like ethylamine. But, and this is crucial, you have to use excess ammonia.
Why the excess?
If you don't, the primary amine you just made can act as a nucleophile itself. It'll attack another halogenoalkane molecule, and you'll get a messy mixture of secondary and tertiary amines that you never wanted.
So you flood the system with ammonia to make sure it's the only thing doing the attacking.
That's the idea. And this all leads us back to the big question. How does the structure, primary, secondary, or tertiary, influence how the substitution actually happens on a molecular level? This brings us to the two key mechanisms, SN2 and SN1.
Okay, let's start with primary halogenoalkanes. They're structurally simple, not very bulky, so they favor the SN2 mechanism.
SN2. That stands for substitution, nucleophilic, bimolecular. It is a single-step, what we call a concerted process. The primary carbon is relatively exposed, so the nucleophile attacks from one side at the exact same moment the halogen leaves from the opposite side.
So bond making and bond breaking happen at the same time.
Yeah.
A simultaneous attack.
Precisely. And because both molecules, the halogenoalkane and the nucleophile, are involved in that one single step, the reaction rate depends on the concentration of both of them. That's what the 2 in SN2 means.
Now, tertiary halogenoalkanes are the opposite. They're bulky, they're structurally hindered, so that direct simultaneous attack is impossible. They're forced to take a totally different route.
The SN1 mechanism, substitution, nucleophilic, unimolecular. This one is a two-step process. In step 1, which is the slow step, the carbon-halogen bond just breaks on its own.
It just snaps.
It snaps. Through heterolytic fission, the halogen takes both electrons and leaves as a halide ion. This creates a highly unstable intermediate called a tertiary carbocation.
And that slow formation of the carbocation, that's the rate-determining step.
It is, and
Oh.
because only one molecule, the halogenalkane, is involved in that slow step, the 1 in SN1 tells us the rate depends only on the concentration of the halogenalkane. Step 2 is super fast. The nucleophile just immediately attacks the positive carbon of that carbocation.
So why is this SN1 route only really possible for the tertiary molecules?
Because tertiary carbocations are much more stable than primary ones. That positive carbon is attached to 3 alkyl groups. These groups donate electrons towards that positive center. We call it the positive inductive effect.
So they help to spread out and stabilize that positive charge.
Exactly. They reduce the charge density, stabilizing the whole thing just long enough for the reaction to complete. So you see, the structure dictates the mechanism, which in turn dictates the kinetics.
That is a brilliant way to put it. Okay, we focused heavily on substitution. But what happens if we change the conditions? Can we get a totally different product?
Absolutely. If we change the solvent, we can trigger the other major reaction pathway, elimination. This time, we're losing a small molecule, a hydrogen halide, HX from the compound, to form an alkene.
So bromothane loses HBr and becomes ethene.
Correct. And the crucial condition change here is the solvent.
You can't just use water.
No. The key is using ethanolic sodium hydroxide, NaOH, in ethanol and applying heat. In this less polar, non-aqueous environment, the OH ion acts mainly as a strong base, not a nucleophile.
A base being a proton acceptor.
Exactly. It plucks a hydrogen ion off a carbon next door to the one with the halogen. The electrons from that CH bond then swing over to form a double bond, and the halogen gets kicked out.
That's wild. So you're telling me the difference between getting an alcohol and an alkanen is literally just whether I put water or alcohol in my beaker. That is incredible leverage.
It is the single most important distinction in this whole topic. If you use aqueous sodium hydroxide, you get nucleophilic substitution. You make an alcohol.
Okay.
If you switch to ethanolic sodium hydroxide, you get elimination. You make an alkene.
Amazing.
So, to quickly recap the absolute essentials from this deep dive. First, reactivity is all about the CX bond strength. Iodoalkanes are fastest because that CI bond is the weakest.
Right.
Second, the polarity of that CX bond makes the carbon atom a target for nucleophiles. Third, primary halogenoalkanes use the single-step SN2 mechanism, where the rate depends on both reactants.
And fourth, tertiary ones use the two-step SN1 mechanism, which goes through a stable carbocation, so the rate only depends on the halogenoalkane itself.
And finally, and most importantly, the solvent dictates the entire outcome. Aqueous gives you substitution. Ethanolic gives you elimination.
So what does this all mean for the big picture? I mean, the seemingly simple choice between using an aqueous or an ethanolic solvent just completely changes the product you make. You have to consider the industrial implications of that. How often is a simple solvent change the key to switching production between, say, a vital alcohol and a necessary alkene in chemical manufacturing? That's something to think about as you review these mechanisms. Thank you for joining us for this deep dive into halogenoalkanes. From the entire Last Minute Lecture team, we really appreciate you taking the time to learn with us.